Now we're going to talk about another subject. We've looked at numbers. Now we're going to look at something called the language of mathematics. And this is a topic that really needs a little bit of discussion, because when you learn mathematics, you have to realize you're really learning a new language. And to become fluent in it, you ought to have some idea of how it operates. So the first thing we're going to look at here is learning to read mathematics. So here are a few facts about mathematics you need to know. Mathematics. And you notice when I write it, I'm writing it with a capital M, just like you'd write English or German or French or Spanish with a capital letter. Think of it as a language for the time being. All right, mathematics. First thing you need to note is that it is primarily a written language. Now this is very much unlike all the natural languages, which start out as spoken languages. Primarily mathematics is a written language. What is it designed to do? Well, it is designed to discuss easily the following kinds of things. 1, basic objects. And what I mean by that are basic mathematical objects, mental objects if you like. What kind of objects am I talking about? Well, I'm talking about numbers, as you've already seen, sets, what we'll later talk about, functions, etc. It is a language that is designed to discuss basic objects easily. What else is it designed to do? It is designed to discuss operations on these objects. So operations on those objects. Now that is extremely important. That is really what algebra is about. What do I mean by operations? Well, let me give you some indication. Addition, subtraction, multiplication, division. And that all happens of numbers. But those are not the only kind of operations. Composition of functions. When we study functions later in the course, you'll find out what that means. But that's an operation you can perform on functions. What else? How about union and intersection of sets? Sets we've talked about a little bit. We didn't discuss union and intersection, but those are operations on sets, etc. So mathematics allows us to discuss with ease and in a written form basic objects and operations on those objects. Now, what else can we say about the mathematical language? Mathematics, again with a capital M, mathematics has a new language feature. Now this is a feature that the natural languages that we all know don't have. This is a new language feature. And you can write it in several different ways. You can say it is the notion of placeholders. Or another form is to say dummy variables. Placeholders is the one I like for the time being. And let me show you exactly what I mean by writing down an example of a statement in the language of mathematics that illustrates this aspect. Example. In mathematics, you can write down the following statement. 3 times x plus 4 equals 3x plus 12. Now that should be easy to see, that if I multiply 3 times x, I get the 3x. 3 times the 4, I get the 12. So this statement is true. But notice the following other statements. 3 times a plus 4 equals 3a plus 12. Or even more generally, 3 times box plus 4 equals 3 times box plus 12. In mathematics, these are all the same, right? It doesn't matter what the letter is or whether I use another symbol there. It says the same statement in each case. Now you try that with a natural language. Go in, choose a word or a sentence, and change the letters or change the words. It is unlikely that you would end up with a sentence of the same meaning. So mathematics is very different in that respect. Now, what does it take to learn to read mathematics? Effort. Well, you already knew that. Practice. And I hope you also had a sense of that. Imitation. Well, you know what this is sounding like. It's sounding like exactly the kind of thing they teach you when you're learning another language. Well, mathematics is a language, so you might expect that that's going to be the case. What kind of words are used to indicate this? What are key words that you might hear that suggest that there's a language involved? Key phrases. Organized work. Your instructors are always saying, make your work organized. The phrase standard, forgive my spelling there, standard form. We have standard forms for certain expressions in mathematics, as we will discuss later in the course. Another word, another phrase, complete mathematical sentences. Now, once you start thinking of mathematics as a language, to say complete mathematical sentences is not a nonsense statement. We will talk more about this in a minute, because sentences have certain aspects to them. They have nouns in them, they have pronouns perhaps, they have verbs in them. So these are phrases that describe the kind of work that needs to be put in to learn mathematics. Now let's go ahead and look at some of the symbols and some of the words that are used in this language called mathematics. So some symbols of algebra, and we'll look at a couple of words also. So, some symbols and words of algebra. Some of these you've known for a long time, but I'll make a few remarks as we go. You know that symbol from grade school, from elementary school. This stands for the addition of two numbers. You also know this symbol, which stands for subtraction, if it's an operation. You also know that it stands for negation, because we've seen on the real number line this is an indicator to go left. In this course, we will use a dot for multiplication. Multiplication. And on this topic, let me put here, do not use the X, which is the elementary school version of the multiplication symbol. The reason is simple, it looks like the variable x. And it has actually survived in many places, sometimes in scientific notation, and sometimes in other places you'll see the x occur. But we will tend to use the multiplication, or we will put two numbers or variables next to each other to indicate multiplication. All right, let's move on. Division. Now see, I wrote the word before I wrote down any notation. Here's the way you want to write division if you're writing by hand as much as possible. A line that's horizontal, and then you will put something on the top and something on the bottom. And why don't you go ahead and call that the top and the bottom? If you actually look through the history of our notation and the words we use, you'll find out that when we call this a numerator on top or a denominator on the bottom, that just means top and bottom. So there's no reason we can't use that terminology here. Now division also has another way of being written with a forward slash. Now that's often written when you have to write things all in a single line. But when you're doing your work by yourself on paper, you're going to want to write it horizontally or vertically rather as much as possible. And just for the record, do not use the old notation for division like so. All right, we will not need that. All right, there are some other symbols that are used, and we'll explain them more later in the course. But let me just introduce them here so you will have seen them. There is this symbol, sometimes with a number in front. These are often called radicals. And radical, of course, is a word meaning root, and that's what these are about. Now, where did this come from? Well, let me give you at least a pseudo-history of where this may have come from. It originally looked like that. And what did that come from? That probably was the result of writing down the letter R. R for radical, or root. The R becomes transformed into something that looks like this, and then finally into something like this. Now, you may notice here that I've done something that seems a little unusual to you. I put a little tail. I call these tails on the end of my root symbols. That tells me where the root symbol ends. So I'd like you to do that as much as possible. You will see me do it throughout the course, so It should be fairly common by then. What other sorts of symbols do we see very often? Well, there are the grouping symbols. Parentheses, square brackets. See, we've already seen these. We've also seen the curly brackets or braces. These might be called grouping symbols. They allow us to talk about a bunch of things. An interval perhaps, open or closed, a set of objects, etc. There are some other symbols we will encounter. I'm not going to give you an entire list now, but there are a couple of things that we'll see. We've already seen, or will see, this symbol. And it goes the other way also. Remember, this is the greater than or less than symbol. It doesn't matter which is which. Remember that the big side is the larger number, and the small side, where the point is where the small number goes. So it doesn't matter what orientation it is, as long as at the point is the small number and the other side is the big number. So one might write 2 is greater than 3, but you can also write that 3 is less than 2. Except that that's not true, and that would make you unhappy, wouldn't it? So let me show you another notation. This is where you put a slash through when something's not true. All right? What I meant to say is 2 is less than 3, or 3 is greater than 2. There, I'm redeemed. All right, let me give you a couple of words of mathematics that we use a lot and tend to be sloppy about, at least students seem to be sloppy about. Terms and factors. These are very simple ideas. Terms are things which are added. And factors are things which are multiplied. That's it. That's all there is to it. Use the words correctly, as you would in any language, and you'll be better off because people will understand you and you will understand what it is you've written. Back to symbols. Here's a famous one. I've already used it all throughout this course. It's the equal symbol. Equals, or equal to. Sometimes we say equivalent to. But those are two ways of phrasing the equal sign. There is another important symbol that is becoming more and more common, and I want you to get used to it. It's like the equal sign, except that there are two wavy lines. What does this mean? Well, this doesn't mean equals. Equal lines are nice straight lines. When they're wavy like this, what we mean is approximately. Approximately equal to. These are very important when you have calculators around, and we will use this throughout the course. Let me show you an example of how this might be used. I might say that square root of 2 is approximately 1.41. That's the wrong answer if it were an equal sign, but as an approximation it's perfectly good. I might also say that pi is approximately 3.14. Again, if that were an equal sign it would be wrong, but as an approximation it is perfectly good. And so on. Now, here are two pieces of notation that are vital to understanding mathematics. And students don't see it early enough, so I'm introducing it here. This is an arrow going from left to right. It will be used in theorems and means implies. It also means the phrase if ... then, where if would appear on the left of the arrow and the then would follow the arrow. If you have an arrow going from left to right and also one from right to left, then you can put them together into a double arrow. This is usually referred to as double implication. It sometimes is stated verbally or written as if and only if. So when you see this, you should translate it as to a double arrow. There's a symbol for that that's become common, IFF. And you might also say is equivalent to. So this says that two statements are equivalent. Now, in a moment I will show you how these are used in actual statements of mathematics. But let me continue on with my list and say a few words about letter conventions. Letter conventions. Why do mathematicians choose letters to stand for certain kinds of things? Well, these conventions are due to Descartes. So I won't claim any originality for them. These have been around quite a while. Here's the letter conventions as a rule. Of course, they're not always adhered to. These are only conventions. These are not absolute laws. A, B, C, numbers toward the beginning of the alphabet, usually stand for constants when we're doing mathematics, algebra. The numbers in the middle, like I, J, K, L, M, N, and so on, these often stand for integers. In fact, they often stand for positive integers, numbers like 1, 2, 3, 4, etc. And finally, at the end, those variable letters X, Y, and Z, these stand for variables. So these are the unknowns, the X, Y, and Z that are living underneath my head here. X, Y, and Z. These are often used for the unknowns, for variables that we would like to discover in the process of solving our equations. So A, B, and C stand for constants. I, J, K, L, M, and N. Those middle numbers stand for integers. And finally, the X, Y, and Z stand for variables. All right. Well, let's go back to my list, and we'll talk about the next aspect of the language of mathematics. Nouns, pronouns, and the main verb of algebra. If we're talking about mathematics as a language, there have to be these parts of speech. So let's talk about them. First, let's talk about nouns. What would nouns be in mathematics? Nouns are equal to number expressions. Because nouns are things that always have the same meaning. For example, 5 is a noun in mathematics. 4 plus 12.3 is a number when the addition is done, and that's also going to be a noun. 3 squared, for example, or something more complicated, 3 times 7 minus 9 plus a half, etc. All of these are nouns. They have one and only one meaning, even though a little effort might be needed to write them out as a single number. Okay, what else did I suggest? Pronouns. Pronouns. What would be pronouns? Well, these are things that stand in for nouns and can be replaced by nouns. So these are going to be what we call variable expressions. See, these work just exactly like pronouns work. For example, 3x plus 5 is a perfectly good mathematical pronoun. If you put in a variable, a value for the x, then you get a noun. Here's another one, a times b. Put in values for a and b, it becomes a noun. As it stands, it's a pronoun. U squared minus v squared, etc. All of these are legitimate mathematical pronouns. If you fill them in, they become nouns. Now, let's come to the main verb of mathematics. There's one main verb. I think you know what it is. The main verb is equals. And with this verb, I can now define a sentence. A specific kind of sentence. Definition. And equation, one of the most important sentences we talk about, is a declarative sentence. Remembering your grammar, is a declarative sentence in which the verb, as I said above, is equals. That's what an equation is. It is a sentence. Sentence, and the verb is equals. So when you write down equations, we want to be careful to write out complete mathematical sentences. We want it all to make sense. So you'll see the notation that I use and the way I express things, the way I organize my work, and the way I use standard forms. All of these will be because I'm trying to preserve my sentences. All right, let's go back to my list and look at my final topic for the language of mathematics. Theorems, corollaries, lemmas, and all that. What are all of those, and why do mathematicians use all those odd words? Well, let's see here. Let me write these down. Theorems, corollaries, lemmas. Propositions, there's another one that's used. And so on. What are all of those? These are simply statements of fact in mathematics. That's all they are. They're a way of writing down a fact. Why are all these different words used? Well, for historical reasons. Is there any different meaning to them that we ought to discern? Well, a little bit. Theorems usually mean some kind of fairly major result. Corollary is a theorem that follows immediately upon another theorem. So it's a trailer, if you like. A lemma is often a smaller result. A lemma or a proposition are usually smaller results that don't really warrant being called theorems. They're tiny results, they're still facts, they're just a little bit less important. So there's a kind of hierarchy for the use of these words. This is not hard and fast, but I think that if you realize these all are just statements of facts, that none of these words will bother you. All right, what do these facts look like? There are two main forms that these theorems, corollaries, lemmas, etc. come in. So two main forms of what I've called up there generically facts. What are the two main forms? The left to right arrow form and the double arrow form. I will give you one illustration of each one. In other words, I will write down a very simple theorem that indicates a left to right argument and one that indicates a back and forth statement. These are both statements. So here's an example. This is, if you like, we'll call it a theorem. Very simple result. If, remember, the arrow can be rewritten in English as if and then a then follows. If A and B are odd, you remember what odd numbers are? Odd natural numbers. Then A plus B is even. Now there's the theorem. And notice it's a one-directional arrow. If this statement holds, then this statement follows. And this is not a hard theorem. This is one you know already. If you take two odd numbers and add them together, like adding 3 and 5, you get 8, which is an even number. That will always work. Also notice that this doesn't work in the reverse direction. Suppose you add two numbers and get an even number. That does not mean that A and B are even. For example, if I take 2 plus 6, those are both even numbers. They add up to 8, which is an even number, but neither 2 nor 6 are odd. So the theorem does not reverse. So this is a one-directional result. Now if you see this when you see theorems, this will help make clear how to use these results. You must have the if in order to draw the then conclusion. Now here's an example of the other form. Example, here's another theorem. I guess I should have called it a corollary or something, just to vary the name of it. Let's call this a theorem. And here's how this will go. For any numbers, you can assume I mean real numbers here, x, a, and b, the following two statements are equivalent. X plus a equals b. There's one statement. That is true. This is equivalent to the statement that x is equal to b minus a. Now this is an example of a double arrow theorem. And again, this is easy enough for you to see why it's true. I don't actually have to produce a proof. X plus a equals b is the same as this because if I started at the top, if I subtracted a from both sides, on the left I would have x, on the right I would have b minus a. That's what this says. And reversing it, if I start with x equal b minus a, if I add a to both sides, on the left I get x plus a, on the right I get b, which is what the top says. So these are, in fact, equivalent statements. So I can start at either place and go to the other. That's what the double arrows mean. So there's an example of a double arrow theorem. The one before, which I'll return to here, is an example of a single arrow theorem. These are the only two kinds of theorems there are. So when you're studying mathematics and you come across theorems, lemmas, corollaries, propositions, etc., you realize there are only these two different kinds, this one and the double arrow kind. All right, well, that's all I have to say about the language of mathematics. You should spend some time trying to become familiar with the symbols and the suggestions I made about nouns and verbs, etc. And then after this, we will move on with basics.